Let's look at example 10 and 11. These are the last two examples in this chapter, and these two examples deal with linear motion. So that's one of the applications of calculus. So let's see what this one has for us, and we can use a calculator here. Particle moves along a horizontal line. The particle's displacement in meters from origin is given by the displacement function, and t is in seconds. Okay, A, find the particle's velocity and acceleration. So we've done this many times. Velocity is the derivative of displacement. So we have 5 becomes 0 when we derive it. So we got positive 2 sine, because the derivative of cos is a negative sine, 3t. But we got a times by 3 because that's the derivative of 3t, which gives us 6 sine 3t. And then our acceleration function is, oh, that's not part B, the derivative of velocity, which is 6 cos 3t, times 3. I should probably do this. And we should get 18 cos 3t for the acceleration. Okay, that's A. Now B, find the particle's initial displacement, velocity, and acceleration. Right, so that's all when the time is 0. Initial time is 0. Alright, so sub in each of these into your functions, and you should get 5 minus 2 cos 3t is 2 cos 0, which is 2. So displacement should be 3 meters. Velocity should be 6 sine 0, which is 0 meters per second. And A should be 18 cos 0, which is 18 meters per second squared. Interesting. So initial displacement is 3 meters from the origin. It's not moving, but it's got an acceleration of 18 meters per second squared. All right, let's continue. Okay, let's have a look at C. Find when the particle is moving to the right, to the left, and stopped during the time from 0 to pi. Okay, so this one gets a little bit tricky, but so we can do it by hand. But since we can use a calculator, let's just graph this function and think about the function that you're going to graph, right? So we should graph the velocity function here because when it's stopped, all right, think about what this means. All right, velocity is 0. So when it's moving to the right, velocity should be positive, and if it's moving to the left, that's when the velocity function is negative. So we should graph the velocity function first on the calculator. So 6 sine 3t or 3x, that'll give it to us. And let's change our window from 0 to pi because that's all we're interested in. Okay, now all we need to do from here is find the zeros first, all right, because this is when, these are the points where the particle is stationary, it's not moving. So analyze graph, find all your zeros from 0 to pi. Yep, we have a 0 at pi as well. All right, there we go. Maybe just zoom out a little bit. Okay. Let's make this a bit easier to see. Whoops. What happened there? I don't want that. I want to move this. There we go. Okay. Now let's clip this into here so we've got something to work with. Alright, so let's answer the question. Now, let's just start with when it's moving to the right. So the particle, and we can see this from the graph. Right. In the intervals. So in between 0, t. Now, since this is a sine graph, we can see 3 sections, I guess, between 0 and pi. So that means the second, that 1.05 is actually pi on 3. So I'm just going to use that. And it's also moving to the right at so our third, that 2.09, our third intercept there that we found, to our final intercept, which is at pi. All right, see how the velocity graph is positive in those sections? It's above the x-axis. That's when it's moving to the right. So the particle, and then now let's do the left. Left in the, I should say over the intervals actually. But you know what I mean. So it's going to be between pi on 3 and 2 pi on 3. And the particle has stopped at t equals 0, pi on 3, 2 pi on 3, and pi. Okay, and finally, let's have a look at D. Write down a definite integral that represents the total distance traveled between 0 and pi seconds, and use the GDC to find the distance. Okay, so remember when we're finding total distance, it's the integral of the absolute value of the velocity function. This is from last term. All right, I'll just quickly explain. All right, so good thing we have our velocity function here. The area underneath the velocity function represents displacement, but since we want distance, all right, we want every single area that we can find. We don't want any negative areas, so the absolute value helps negate the negative area. Well, not negated, but it just calculates all these areas separately without any positives or all positives, and adds them all up. So we get the total distance this way. So let's just use a calculator to figure this out. Distance 0 to pi, absolute value of 5 take 2 cos 3t with respect to t. Whoop, my bad. I typed in the displacement function. Let's do it again. Absolute value 6 sine 3t with respect to t from 0 to pi. 12 is our answer. Okay, so 12 meters is the total distance. Alright, so that's example 10. And lucky last, example 11. A particle moves along a straight line so that its velocity at time t is given by this function. Find the speed of the particle when t equals 5 pi on 6. Okay, let's try not to use a calculator here and put our trig skills to the test. So we want the speed. We've already been given the velocity function, so let's just sub in 5 pi on 6 for t. So 5 sine 5 pi on 6 cos squared 5 pi on 6. Alright, so using our knowledge of exact values, alright, so sine 5 pi on 6 is a half. Cos 5 pi on 6 is negative root 3 on 2, and this is being squared, so we have 5 over 2 times 3 over 4, which is 15 on 8. It's in meters and speed, so per second. Alright, so that's part A. So apply your knowledge of your exact values here. Alright, let's have a look at B. When t equals 0, the displacement of the particle is 3 meters. Find an expression for s in terms of t. Alright, let's do that here. Okay, so we want displacement, so we need to work what we've been given with. Displacement is the integral of velocity, or the area under the graph of a velocity curve. So let's do this first. So we have the integral of 5 sine t cos squared t with respect to t. Okay, we need to use substitution here. So let u equal, I'm going to let u equal cos t. So that means du dx equals, du dt equals negative sine t, and then dt equals du on negative sine t. So we're going to substitute this in. 5 sine t, now it's u squared, and dt we're going to sub in du over negative sine t. Alright, so that means the sine t's will cancel each other out, and then we're going to get a negative 5, but I'm going to put that outside the integral now. So negative 5 times the integral of u squared, so that gives me negative 5 times, alright, it's going to be u cubed on 3, but I'll just do all this in one go. Alright, plus c. Okay, so there's my integral. Now, I need to find out what c is, because I've been told when t equals 0, the displacement is 3, right? So 3 equals negative 5. Now, cos cubed of 0, cos 0 is 1, so this is just negative 5 times 1, which is negative 5, plus c. So that means c equals 3 plus 5 on 3, which is 14 on 3. So therefore, my displacement function is negative 5 cos cubed t. Since they're both, everything's over 3, I'm just going to write plus 14 and all over 3, like that. Alright, so that's B. Bit of a tricky one. Alright, a lot involved there. And C, find an expression for the acceleration of the particle in terms of t. Okay. So acceleration is just the derivative of velocity. So this is where we have to think about what rule to use to differentiate velocity. So we have 5 sine t times cos squared t. We're going to have to use the product rule and also a chain rule in here as well. All right, so let I'll do it this way for this example. So let u equals 5 sine t and v equals cos squared t. So to save time, derivative of u is going to be 5 cos t. Derivative of v, so this is going to be 2 negative 2 cos t sine t. Alright, excuse the working going pretty close to the other part, but if we want to find the derivative, it's uv prime plus vu prime, so that gives us negative 10 cos t sine squared t plus 5 cos cubed t. All right, and there's our expression for acceleration. So again, quite a lot involved there. All right, but this gives you an idea of how you can apply your derivatives and integrals to trig functions in the context of linear motion.